In the last video, I left you with an exercise. Hopefully you work through it so that you'll be in a great position to check my answer as I work it out in front of you. Again, we're starting with a 20 megahertz sinusoidal, which we defined as 20 megahertz. Say we went through a bunch of math and found that the answer that we wanted to look for in polar form, in phasor form, looked just like this here. Now note this 4J isn't exactly a clean amplitude because it's not a real number, it's an imaginary number, so we'll have to do some cleanup there. So let's take it one step at a time. So first of all, we want to convert into a time domain function, and we do that by addressing the fact that earlier we remove this e to the j omega t term. So now we are going to return it. And what that means is before we took out the e to the j omega t, now we're going to add it back. So v of z, and now it is a function of t, is going to be equal to 4j e to the minus j pi z with a new e to the j omega t term that we just put in, and the problem had defined over here that omega is going to be equal to 2 pi times 20 megahertz, which is going to be equal to 2 pi times 20 10 to the 6, which is 40 pi times 10 to the 6. Now note that this term is not just a clean amplitude. We ultimately want to get everything to just look like e to the j theta so that we can use Euler's rule and convert it into the sinusoid form. So you'll note that 4j in the real and complex plane actually looks like a vector that's pointed straight up, which is an angle of pi half with a length of 4. So 4j is actually e to the j pi half as a result. So let's do some combining and cleanup. We have v of zt is going to be equal to 4 e to the j pi half e to the minus j pi z and e to the j omega t. And since we can add exponents, we can combine all of this into one glorious exponential of e to the j omega t minus pi z, I'm switching the order a bit, plus pi half. So as we haven't really changed the symbol, so we know that this is omega. This is our beta. The negative means that it's a forward propagating wave. And our pi half, this is just an initial phase term that just tells you that the phasor is actually in a particular location at t equals 0. That's not just beta, but beta with this extra phase. So it's just an offset. We don't have to worry too much about it. Next up, we now have all of the key terms, so we can convert this back into the time domain sinusoid. So recall that v of zt, if we wanted to get what the actual sinusoid was, we just have to take the real part of what we had calculated here. So e to the j omega t minus pi z plus pi half, which the real part, we knew that the real part of this, if we were looking for the real part, that is simply equal to a cosine theta, because again, if we drew it out with this angle theta and magnitude a, the real part is simply the cosine projection. So doing that, we will know that it's going to look like 4 cosine omega t minus pi z plus pi half, and we can then plug in the frequency value that we had earlier. So 40 pi times 10 to the 6 t minus pi z plus pi half. And that is our final answer. So with these examples, hopefully you have a slight idea, a better idea about what it means to talk about the situation in terms of a phasor, which is simply saying that if we're only focused on a single frequency, we can then just remove the e to the j omega t term, leaving us with something that is just a function of z that we can then write in the form of a magnitude and an exponent. And so by doing, and this simplifies our analysis because it's one less variable that we have to worry about. So once we've taken out this e to the j omega t, we take our phasor, do a bunch of work, and when we want to convert it back into a real-time function that tells us what we'll get at any point in time, we just multiply e to the j omega t back. And the second thing you should be able to do is, once you have something in a complex exponential form like this, to be able to get it back into a sinusoid form using the procedure that we outlined and demonstrated in this example.